Today, we're diving into a new kind of AI, one that's inspired less by pure math and more by how our own brains seem to work. It's an approach that doesn't learn with calculus, but by drawing maps. So let me ask you this. What if an AI could learn, not by crunching endless equations, but by organizing information spatially? Creating a literal map of ideas where similar concepts actually become neighbors? That's the wild and fascinating question behind this whole approach. You see, today's AIs, as powerful as they are, have some real limitations. They can be kind of brittle, breaking in ways we don't expect. They're often total black boxes, which means even your creators don't always know why they make a certain decision. And they have this huge problem called catastrophic forgetting, where learning one new thing can just erase old knowledge. This new idea, though, aims for something much more like us, an AI that's robust, transparent, and can keep learning without wiping its memory clean. All right, so let's dig into that first. This whole black box problem. Why are even our most advanced AIs so hard to understand? Well, most of today's neural networks live in this world of pure, continuous math. Every single part of the network has to be perfectly smooth, or what mathematicians call differentiable, so the system can learn by making tiny adjustments. And while that works, it creates this impossibly tangled web of millions of little numbers, making it pretty much impossible for any human to truly follow the AI's chain of thought. So how do we get around this? Well, this new approach just tosses that whole idea of a continuous space right out the window. Instead, every single concept, whether it's a word or an object, gets its own unique, discrete code. The basic building block here is called a sparse bit vector. Just picture a super long string of zeros and ones where almost all of them are zeros. To represent an idea, like the word apple, the system just flips a few of those zeros to ones. No single one bit means anything on its own. It's the unique pattern, the constellation of on bits, that holds the meaning. And what's cool is, this is actually an idea from neuroscience, where it's called population coding. And this is the secret sauce. The whole system is built on one crucial rule. Similar ideas get similar codes. So the bit pattern, the constellation for apple, is designed to overlap just a little bit with the constellation for pear. And the pattern for red might share a few bits with the one for maroon. This one simple idea is the key to everything that comes next. Okay, so now we have all these constellations, each one representing an idea. But a random scattering of stars is just, well, a random scattering of stars. How do you turn that into a coherent map? This is where the AI puts on its cartographer hat. And the way it does this is it's shockingly simple, but super clever. First, it just throws all those concept constellations randomly onto a 2D grid. Then it picks two random points and thinks about swapping them. And here's the rule. If that little switcheroo brings similar constellations closer together, it keeps the change. The goal is just to lower the map's total energy, which is really just a fancy way of saying, make sure similar things are neighbors. So at the very beginning, as you can imagine, it's just total chaos. It's a random mess of concepts, like colorful TV static, with absolutely no structure to it at all. But then the magic happens. After millions and millions of these tiny, simple swaps, something incredible starts to emerge from that randomness. A beautifully structured map takes shape, where similar ideas have all naturally pulled themselves together into little neighborhoods of meaning. And here's where it gets really mind-blowing. This isn't just a cool-looking pattern. The researchers themselves point out that these structures that form look remarkably similar to something called pinwheels, which are these organized clusters of neurons we see in the visual cortex of mammals, including us. It suggests this whole self-organizing process might be tapping into something fundamental about how intelligence itself is structured. All right, so we've built this beautiful brain-like map of concepts. That's great, but what do we do with it? How does the AI actually use this map to understand something new? Well, it uses something called a detector hierarchy. And the best way to picture this is to imagine laying a whole bunch of virtual lenses all over the map. You've got big lenses, medium lenses, and tiny lenses, and each one is watching a specific patch of the map. When a new idea comes in and its constellation lights up, all the detectors covering that spot activate. So the specific combination of detectors that fire off, from the biggest ones down to the smallest ones, creates a new compact code. This is called a structural embedding. It's not just the original constellation anymore. It's a much richer fingerprint that describes an idea based on its location and all of its relationships across the entire map. Let's make this real with an example right from the paper. Take a look at these Russian words. Words that share a common root, like crasivea for beautiful and crescita for beauty, they light up the exact same core region on the map. But a word with a totally different meaning, like revnist for jealousy, activates a completely different neighborhood. The AI isn't just memorizing vocabulary, it's spatially learning the underlying structure of the language.
Okay, so we've gone through constellations, maps, detectors, but what's the big picture? Why go through all this trouble instead of just building bigger and bigger neural networks?
Well, the payoff could be huge because you can literally see what's happening on the map. You get an AI that's truly interpretable. You can follow its reasoning. You could, in theory, perform surgery on its memory, editing or even removing a specific concept without having to retrain the whole thing from scratch. And it seems this structure makes it naturally immune to that catastrophic forgetting problem and also much more resistant to just making things up, which we all know as AI hallucinations.
This is a completely different way of thinking about AI. It's a real departure from the current path. Now, of course, this is still very early research. There are big challenges like getting it to scale up and perform on really complex tasks. But still, by shifting from pure calculus to a more biological, more intuitive structure, it really makes you wonder, are we looking at a blueprint for a more transparent, robust, and maybe even a more understandable kind of artificial intelligence?